Alright, so I'm going to be talking about the idea of linear approximation. And so the idea of this is that it's a way to approximate a complicated function by a very simple function. So linear functions are basically the simplest functions we know how to do things with, and the more complicated functions, maybe we don't know how to evaluate them without a calculator, or it's just inconvenient to evaluate them. So if we could replace it by a linear function, which is close to that more complicated function, then that would make our lives a lot easier. So the idea is that if we have some differentiable function like this, then at any point A, we know how to find the tangent line of the function. So the point on the line here is a comma f of a, and we know if the slope of this line is f prime of a. So we can write down the formula for the tangent line, which is y equals f of a plus f prime of a times x minus a. This is just from the point slope formula. So this is what's known as the linear approximation to f at a. And so why is this a good thing to do? So the idea is that if x is close to a, then f of x is approximately equal to just this tangent line, f of a plus f prime of a times x minus a. So why is this the case? Well, if we think about this graph, we have our tangent line here. If I look far away from the point A, then there's a pretty big gap between the line and the function that we're approximating. But if I look just in a region around A, and I zoom in on that region, then the tangent line and the original function will be almost indistinguishable. So this is a property of differentiable functions. If you zoom in really far on any given point, they just sort of look like a straight line. And that's why if we find the tangent line at that point, it's a relatively good approximation to the original function. So let's see an example of how this works. So let's suppose we have the function f of x is equal to sine of x. And suppose you want to approximate sine of pi divided by 5. So sine of pi divided by 5 is not one of the common angles that we know, so we can't really figure this out without a calculator. Now, if you do have a calculator, you can plug in this value and find that the exact value of sine pi over 5 is 0.5878, roughly. So the question is, can we get an estimate without using our calculator, which is somewhat close to this? So the closest point to pi over 5 where we do know the value of the sine function is pi divided by 6. So we know sine of pi over 6 is equal to 1/2. So do a linear approximation to sine of x at pi divided by 6, and then we'll use that linear approximation to estimate sine of pi divided by 5. So how do we do this? Well, we're going to use this formula up here for the linear approximation, or equivalently, we're just going to find the tangent line to the curve. So we know that f prime of x is equal to cosine of x. So that means f prime of pi over 6 is going to be square root 3 divided by 2. And so that's going to be the slope of our tangent line. And we know a point on the curve already is pi over 6 comma 1/2, so we can write down the equation for the tangent line. So f of x is approximately equal to square root 3 divided by 2 times x minus pi over 6 plus 1/2. So now, if we want to estimate sine of pi divided by 5, we could plug that into this equation. And so let's see, if we do that, then what do we get? I'm checking on my calculator now. So we get 0.591. So if we compare this to the actual value we were supposed to get, it's not so bad an approximation. I mean, we're off by a little bit, but we're reasonably close. So this is an example of how we could use a tangent line to estimate the value of the sine function at a point that we usually wouldn't know without just using our calculator. So you'll notice, though, there's some error in our approximation. We're off by about 0.004, it looks like, roughly, or 0.003, something like that. So it would be nice to know how much error we're making when we use the linear approximation instead of the original function. So we can't determine the exact amount of error we have unless we actually know the exact value, which we wouldn't without a calculator. But we can say whether our estimate is an overestimate or an underestimate. So if f of x is concave up, then the graph will look something like this. And if we draw a tangent line at any point, you'll see that the values of the tangent line lie beneath the original function. So that means that if f is concave up, the linear approximation will give an underestimate, because the tangent line is beneath the function. On the other hand, if f of x is concave down, then we have a graph which looks something like this, and the tangent line is above the function. So in this case, the linear approximation is an overestimate. So let's take a look at the sine function. So I'm running out of room here, but the sine function, recall, looks something like this. And so this point here is pi divided by 2. So pi over 6 is somewhere in between these things. Sorry, that point is pi, not pi over 2. This point is pi over 2. So pi over 6 is somewhere in this small interval, as well as pi over 5. And we can see that in this region, the function is concave down. So you would expect our linear approximation to be an overestimate based on this claim here. And if we look back at the values that we got, we see that our linear approximation gave 0.59. The actual value was 0.587. So we did indeed get an overestimate using our linear approximation. So this agrees with what we expect from these pictures. So basically, the idea of linear approximation is we replace the function by its tangent line, and we use the tangent line to get an estimate for the actual value of the function. So really there's not much new here in terms of mathematical content. We're just finding the tangent line to a curve, but we're using it in a different way. We're using it to approximate the values of the function.